Hi, I'm Tora Medalino, and this is Lab 5 on magnetic braking with Faraday. So the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of copper, model the magnet/tube interaction computationally, and then compare your computational predictions with your observed data. So this lab uses Faraday's law, which is explained here, and then here's a diagram kind of representing like the coil, like this would be the copper wire, and this would be the magnet kind of coming through it, if that makes sense. And then here's the equation used along with it. Here's the experimental data from what we did in person. So first we dropped the magnet just in the air, no copper tube, and this is how long, from about 1 meter, and this is how long it took for the magnet to fall to the ground. And then we did it with the tube, and we got an average of 13.47 seconds with the tube. In lab 4, the way I calculated the magnetic dipole moment was incorrect, so I redid it with this work shown, and I got 9.95 to be my magnetic dipole moment. Here is my code. We had to change a few things from the starter code to make it align with the resistivity of copper, for instance. And then this length of the tube is actually only 1/10 of the actual length. The code was taking too long to run. So we divided the length of the tube by a factor of 10, and then in the end here, I multiplied my exit time times 10. And then here are my functions I used, and this is just the magnitude of the forces. Furthermore, for the code, we used Faraday's law to calculate the current induced in each ring by the falling magnet. We used the Boyd-Savort law to calculate the force exerted on each current-carrying ring by the falling magnet. We use Newton's third law to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings. And we use Newton's second law to write the position and velocity updating code to model the motion of the falling magnet. Okay, so here's my code with using the magnetic dipole moment that I derived, which I showed you earlier, with 9.95. It was not really working well with the code I'd written before, so I changed these two things, and then in the end I multiplied my time by another factor of 10 to get 469.71 seconds. And then I played around with the code to get a magnetic dipole moment of 1.1632, and this got me exactly to be at 13.47 seconds. So I just tried different magnetic dipole moments until I got 13.47 seconds, and I changed these two things back to how they were before for this part of the code. So my code aligns pretty well with the data I got in the real world, with this being my magnetic dipole moment. Interpreting the simulation, the intensity of the coloring on the tube indicates the magnetic magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions, which color corresponds to clockwise and which is counterclockwise. So from using Lenz's law, which is explained here, we know that red is counterclockwise and blue is clockwise. And just to note, Lenz's law is complementary to Faraday's law. Faraday's law dictates the magnitude of the induced electromotive force, while Lenz's law determines the direction of the current. So they kind of help explain the same things, just different parts of it. What happens to the dynamics of the system when you flip the magnet around? The magnet would fall as before, but the current directions would be flipped. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? So, like I showed you earlier in my computational system, I had to multiply my time factor by a factor of 10. So it was going much faster than it did in the real world. We just had to make that slight change, and then it aligned pretty well. And then real-world data has outside factors like air resistance and human error from using a stopwatch that could have affected the time. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Gravitational force is greater than magnetic force when entering or exiting the tube, but they're equal within the tube. For the discussion, what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So Ohm's law, which is V equals IR, tells us that decreasing resistance would increase the induced current, and this would produce a stronger opposing magnetic field, which would slow down the falling magnet, and this is also caused by the force of Faraday's law, which would increase. So the magnet would slow down when it was falling. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? There would be less current rings within the tube, producing a weaker opposing magnetic field and causing the magnet to fall faster. And that is my lab.